Okay, so this work, convex category and contextuality, it's joined with Jihan Okai. So let's start. Okay, I start with something maybe all of you know. What is a real convex set? So a real convex set is a set like with this operation that if we have two elements in yeah, I can buy the mouse here. So if we have two elements in X and some value between 0 and 1, we get a new element like some weighted average between them, and that is like it's behave like a convex linear combination in Euclidean space. Like we have some properties, some axioms. Okay, I didn't wrote the axiom because it's not important for this talk. So like this axiom, for example. Okay, but it's not have to be inside. Like it's not have to be inside Euclidean space. Okay, so this is the definition of real convex sets. Of course, one can imagine what is the map that preserves the structure. Then we get the category of real convex set. But now, actually, it's done in the first talk. Actually, I was in the first 20 minutes, maybe some of this done, like to define a real convex set as an algebra over a distribution monad. Okay, there is an alternative way to do this. So let's see how we can do this. Okay, if we have a set X, then drx we mean here R is any semi-ring, okay, any commutative semi-ring, okay. It doesn't have to be the non-negative reals, any commutative semi-ring. So dr of x for set x is all the distribution x, okay, values like for every x there is a value in R, but finite of them just non-zero, and the sum is 1. Okay, it's known for everyone. Of course, this construction actually is functorial. Like this, one can imagine how it's how one can define its own maps, not just like if I have a maps, I apply this dr, and then actually we have more. We have a monad here. Okay, it's no monad, it's a distribution monad, but we can do this for any. Now you hear more. Not use this. Good. Okay. So for any semi-ring, we can do this, and we have this monad. Of course, the unit, like we send any object here x to this distribution that give 1 to x and the other 0. We have this multiplication here. It's known like it takes the average. Like if we have a distribution on distribution, we take the average of this distribution via this Q, like the distribution here. Okay, it's known, I think, for everyone. Now we can talk about algebra over this monad. So let me remind you what is algebra. If we have a monad act on C, so then T algebra is an object there with this map. Like actually this useful to define some algebraic structure. Like we have this, actually this by itself is the algebra. This is a free one. And this actually, they give me the specific for, it's have to be pi x even here. Pi x, because this is specific for this x, like give me the relation in x, okay? So it's not to define thing. And with some property. And what is an algebra over the distribution monad? Okay, of course, yeah, because actually I prepared this more before other audience, so I see that all of you know algebra. The algebra appears in many talks today. So, okay, let's continue with this proposition, important proposition, that the category of real convex sets is isomorphic to the category of algebras over the distribution. Now, when we take the semi-ring to be the non-negative real, okay? So we can define, like instead of define by this way, like to say this is a real convex set, we can say just dr algebra. And now one can define, it's in general, like how it's appear in the duality of for convexity. Maybe it's appeared before also, I found it's there for Park Jacobs, that he defined R convex set when R is any commutative semi-ring in this way. We say is a D algebra in the category of sets. Okay. Okay, we take now this point of view in order to define convex category. This point of view. So we have to show that this DR, the distribution monad, act on categories. So how it's acting category? Okay. If we have a category, of course, locally small category, we define a new category, DRC. The object is the same object as C. And the morphism is like we apply the distribution monad in every home between X and Y. Okay, this is the motivation. So how the composition look like? The composition is as the following. If we have a distribution here on this, like this is the map from X to Y in this new category. This is the map from X to Y, morphism from X to Y. This is the morphism from Y to Z. This is distribution here. Then by convolution, like what expected by convolution, like we get a map from X to Z. What's the map? Distribution on all the maps in C from X to Z. So if I have a map, we take like the probability to go from to go through F, right? This is the we know how this is the probability to go from X to Y, all the maps to go from Y to Z. Which ones we get F by composition? Okay, we did this. Okay, so actually this define a functor. This define a functor on category, like define from category to category. More than this actually is the monad on the category of small categories. Okay, this is the monad, and one can imagine what is the structure here. Actually it's not maps now functor, but it's natural, of course, like natural in this word. Okay, so we have the unit. One can actually the two functor. This two functor actually is identity on the object, and it's behave like the distribution monad in home on the morphisms. Okay. Now we can get the following definition as expected to convex category. It's just algebra over this monad. Okay, they are algebra because when it's act on categories. Okay, this is the definition. Okay, but what it means, this definition actually, what that mean to be? First of all, that means that every home set between X and Y, all the maps between X and Y. Here I mean that if C is convex category. If C is a convex category, what does this mean? First of all, this is a category, but every it's R convex category in the sense that it's DR algebra. Okay, every CXY is R convex. Like we have such structure map, but more than this, actually this behave good together. Like if I have XY, I have YZ, so this behave good together in the following sense. Okay, like if I have here some distribution on this, and I have distribution on this, then I can do here because it's convex. I can do convex combination. Like I have a meaning for this as one map. There is a structure pi. If I do this and then compose in C, the category is the same as to do the convolutions that we described before, and then we have the meaning of this during Y. Okay, by this. Okay. So maybe it's remind you category enriched by convex set, right? But actually it's something weaker. So we have the following facts, following propositions, that a category that enriched by R convex set is convex category, okay? But not every convex category is enriched by convex set, okay? Not, for example, this is important example, the Kleisli category of the distribution monad on sets. This category actually is R convex category, but it's not enriched by convex set. Like the Kleisli composition actually satisfies this, the Kleisli composition. Here, if it's Kleisli composition, one imagine with this, it satisfies this, but the Kleisli composition, it's not convex. The Kleisli is not convex. To be enriched by convex category, it have to be that the composition is convex, right? But the Kleisli composition is not convex. So this is the actually other things like are convex sets also. It's by itself convex category. Okay. Okay, let's now move. Okay, we define what is convex category. There is any questions? It's clear what is convex category? Okay, now we move to quantum contextuality. Yes.
Here, what you call convex function or convex path is something that preserves these weighted sums, right? It's like a usual function.
Yeah, but in general, like you don't have weighted sets. You think about this as DR algebra. So it's in this word of DR algebra, morphism is this word.
Like the algebra is something where you have a way to give a meaning to the weighted sum with the weighted for sigma hybrid, right? Of morphisms. And for a set, it would be of elements, for a category, it would be of morphisms. Okay, so convex morphism is something that just commutes with weighted sums?
Yeah. So here, you can see that this exactly, like I just defined this when I remind you the exactly here. You can see, like suppose that this is dr. So this is actually something that commute with this. You see, my friend? Yeah, commute with this. Like suppose that this is dr. Yeah. Kleisli composition. Yeah. It's not. Yeah. You can check. No, I will check. Yeah. Not hard to see. Yeah. You can see. Yeah, I think it's appear in the paper. Maybe I show this is a paper. Yeah, something like this. I don't remember now. Sorry. Okay, let's back. Now we move to quantum contextuality. So I want to describe, maybe some of you don't know, or there is another, many actually point of view to this thing. So I want this point of view, like if we have here three experiment. Okay, if we have three experiment, A, B, C, and that every experiment has two outcome. Like it can be plus, minus, okay, 0 and 1, let's say. Okay, every experiment. And we can do this three experiments, like physical experiments. We can do it as much as we want, but for some reason, like we can measure three of them together. We can just measure two of them. Okay, suppose we have this situation. So then, okay, we can like take A and B, like, okay, do the three measurement 1,000 times, but just measure A and B, okay, and get this probability table, okay, like when they get 0, 0, when they get 0, 1, when they get, and we can do the same, like do this maybe million times. It's easy to do this experiment like as much as we want. And we just measure B and C together, because we can measure just two of them and get this probability table. The same for AC. Okay, so then we get this probability. This is what we know. And what is the fact about this probability table? Of course, the sum here is 1. The sum here is 1, of course. But the other fact that people see in this experiment, that we have this, like if I want to know when we get 0, when I measure E, what is the probability? So I get the sum of this, right? But I can do this in the constants in the context with B or with C, right? Like I can take P1 plus P2, or I can take S1 plus S2. This will be the same. Okay, this will be the same. This is called non-sig. Like there is some physics explanation for this. But the surprising thing that even though we do the three experiments together, together, there is no what called like there is no one probability table for three of them. Okay, like we don't have something like this global probability table for them. Like this probability table sometimes not coming from this. There is even some experiment like this. but even though, you know, like we did 3 of them together, but we don't have the ability to measure 3 of them together, but we just measure 2 of them. Okay, but maybe like someone measure all of them. We know that there is a result for 3 of them, but surprisingly, this is what happened. That it's not coming from, like if we have this, then from this we get this, right? From this probability table, like 0, 0, I can get all the 0, 0 here, like this plus this give me this, right? If we have this, but sometimes it's not coming from this, okay? So this is something that people start to study mathematically, and many approaches, there is many approaches for this. Here I would choose the approach that, Simplicial approach that appear in Simplicial quantum contextuality paper. This paper for Jian Okay, Salman Ipik, and me. So in this approach, actually, one can see that the table of probability here for this specific experiment is exactly a map from this space. I mean by space simplicial set. It's not, maybe it's not known for everyone here, simplicial sets. Sorry, I did prepare for this, right? Just a minute. Okay, simplicial complex, I think everyone know, right? Simplicial complex. Yeah, simplicial set is like we put here, it's algebraic way for simplicial complex, like we put here all the 0 simplexes. Here we put all the 1 simplexes here. And the relation, like we have, of course, here 2 faces maps, right? Like this. We have this face and this face. For triangle, we have 3 faces maps, okay? Like this, this structure is called. We have, of course, the degeneracy map, like when we can think about point in one way as, okay, forget about, there is other maps, so forget about this for a while, okay? So this is simplicial sets. And the nerve, maybe if one knows what is the nerve of a category, so one can think about this Z2 as a category, okay, nerve of Z2. Someone don't know what we mean by nerve of Z2. It's like this structure, but we put here, sorry, point, Z2, 2 simplexes look like this, okay? This is what simplex, and okay. We have these faces maps and, okay, and degeneracy map, okay? And what we mean by DR, we apply distribution here everywhere, okay? Also in this faces map and degeneracy map, we apply the distribution factor. Okay, this is what we mean. And one can think a little bit like exactly this table is exactly a morphism, simplicial morphism from this X, this space. Like, I mean the realization of this X, like there is just 3 2 simplex, okay? 3 2 simplex in this one. And this is the compatibility here, like they have one edge. Like suppose that this is A, this is B, this is C, the experiment. And here when we do 2 together, okay? So the map, like 1 simplex here, 2 simplex, sorry, here, going to DR of this distribution here. So this is exactly a table that we had before, okay? What is the compatibility here? Because it's simplicial map. This gives us the compatibility, okay? Because this is a simplicial map. Okay, so this is one approach of this, and the global distribution, one can imagine that a global distribution like this here is exactly distribution on this. Like we take a map from this to nerve of Z2. What is the map? Like a map from X to nerve Z2, one can imagine like it's just, if I take 0 or 1 for this, 0 or 1 for this, 0 or 1 of this decide what is the map. This determines the map, okay? So this is exactly what we have here above, okay? And the distribution here, this is exactly global distribution. And of course, there is a map, there is a natural map from global distributions that give me these tables, okay? Okay, this needed time to explain this, but this is one approach to this, like we have measurement scenario X, we have outcome space, okay? This is, okay, scenario, measurement space, outcome space, and we have this map that from globals to here, okay? Okay. So in general, we can have any measurement space X and any outcome space. It does not have to be the nerve of Z2, okay? And now we can define what is to be a classic some distribution that is a classic, like it's come from classic word, like in classic word, what I want to say, I didn't say before, in classic word, it doesn't happen. Like every things like this in classic physics, it's coming from a global probability. But in quantum physics, it can happen, something like this. Yeah, so that's why we have the following definition. Some distribution, it's called the classic or non-contextual, if it lies in the image of this map. Like if this distribution here, like the tables come from global distribution, okay? Then this is called the classic. If not, it's called contextual, okay? This is contextuality, sorry. Okay, and now I want to relate between this phenomena and convex category. Okay, how much time I have? 10 minutes? 10 minutes, yeah. Okay. So let's see, the first things, we all know this, okay, this appeared before, Ellenberg-Moore adjunction, all of you know, I think. Yeah, it's appeared before in the talks. So this is the Ellenberg-Moore addition for this DR distribution monad when it acts on category. Here's the convex categories, okay? We forget and go to category. Here we apply DR, we get the free convex category, okay? We have this. Now we also, I mentioned it before, like the monad, DR also act on simplicial sets. Like what I said here, that what I mean by DR of nerve of Z2, DR act on this, like, okay? I apply DR everywhere. Okay, but it's actually a monad. It will be a monad like this. So we can talk about the Kleisli category. This Kleisli category when DR act on simplicial set, and this functor that appeared in the first talk, yeah, this non-functor to the Kleisli category, from the category to the Kleisli of this. This is the formula for this functor. Now, we know that this functor is good to do the adjunction for the Kleisli, right? But no, now think about this functor as a functor in the world of categories, of small categories, okay? And now we take the adjoint of this here, like this appear here. This functor actually is here, right? So we take, sorry, yeah, we take the adjoint of this. So then we have the following proposition. The transpose of this functor with respect to the following adjunction. What happens? It's me? Okay. Okay, the transpose for this functor with respect with this adjunction that appear above is exactly is a functor, okay? I called it theta because it's exactly the theta that appear here, or morphisms. Like, because if we back here, how the theta look like? Here I wrote it when we have in here, but this can be any y here. So it's exactly to the Kleisli, right? Here appears the Kleisli, the morphism of the Kleisli, and here for the free, right? For the simplicial sets, I apply DR, the free category of simplicial sets, the free convex category. Okay? So this theta that appear above is exactly like part of the morph, is theta on the morphisms of such a functor. Which functor is this? Exactly the transpose of this functor, this important functor. Okay, maybe this is actually good, but not have much application. The things that have application when we talk about convex monoid. So what is convex monoid? Of course, it's a convex category, like R convex. Okay, when I said, I mean here for any commutative cell ring, is a convex category with a single object, with one object. But what it means really? Like it means that we have convex sets like this with a structure map but such as this structure map actually is a homomorphism of monoid. This is what it's mean to be convex monoid, okay? Okay, when we have convex monoid, we can talk about something called weak invertibility. What it's mean, like when we have, because it's monoid, actually it's not have to be convex here to define the group of invertible elements, right? But we can ask which element in M like can be a linear combination of a convex combination of the invertible element, okay? This is what it's mean to be weakly invertible, okay? It's not invertible by itself. Of course, every invertible is weakly invertible. It's not invertible, but it's coming from this. Okay, we define here for in general for a general semi-ring. So, because it's this inclusion of the invertible here, this induce inclusion when we apply dr, and we have this structure map. So we ask which element here is in the image of this, okay? Example of a convex, example of a convex monoid is this. Like why this is a convex monoid actually, when we have Y is a simplicial group here. I like the nerve of Z2, by the way, it's simplicial group. It's not just simplicial sets. Like what we mean by simplicial group, like every level, it's a group, and the faces map and the degeneracy map are homomorphism of a group, okay? We can always do about simplicial topological space, simplicial sets, so, okay, so we can talk about it. Okay, so when this is a simplicial group, this have also a monoid structure. Why here actually Y is simplicial group, then dr of Y is a simplicial monoid, will be with the convolution. And then because here there is a structure, group structure, then in this there is a group structure. Monoid structure, okay? So this is monoid. Maybe the hard thing here to prove that this is convex. This is not easy when we talk about convex in this sense, like as a DL R algebra, okay? But actually this is a convex monoid, this one. But we know that here is the distribution that appeared before, and we can talk about contextuality of such a distribution, right? But actually these two notation agrees with each other. So here is a important theorem, the main theorem, that if we have a zero-sum free semi-ring and integral, it have to be integral semi-ring also, and simplicial group X, like the the measurement space is simplicial sets, any simplicial set, but the measurement, the outcome space is the simplicial group, then any distribution here is non-contextual or classic if and only if it's weakly invertible. Okay, so in this case, usually this actually when we take, like we saw in the experiment, like we replace it by the nerve of Z. We take it to be the nerve of Z2, right? Or if we have more outcome, like N outcome, we can put a nerve of Zn. Usually we take this, but we can take any simplicial group, and the notation agrees here of weakly invertible and non-contextuality. And this actually, this have more application actually. We have now physics papers that we apply this more than the previous proposition, because this is a new point of view of the contextuality. Actually, in this is a convex set, okay? This is actually a polytope in general, like when X is finite, this is a polytope. And in this polytope, it's not just convex, there is structure, multiplication structures there. We can do multiplication between distribution in a nice way, like that, nice with the convexity, okay? And this can be applied, I think, in the future. Okay, thank you. Thank you for listening.
I have one.
No one have any question. No.
I have one.
Yeah.
Okay. So the definition of weakly invertible is kind of abstract. So if we think about a concrete probability distribution, what is that?
What does that translate into?
Concrete probability distribution. What do you mean? Like tables before?
Yeah. So let's pick R to be the real interval, unit interval.
What it's mean to be weak invertible? What means the multiplication to be? Like here, for example. Yeah, actually, you take here, in this case, it can be, first of all, it's important because it can be for every convex monoid, not just for this, but for this, actually, you take you have to take all distribution like this, okay? In all distribution like this, you find the invertibles. The invertible, actually, we know what is the invertible. The invertible is exactly, people know quantum, the deterministic here will be. Actually, this is the main thing. Like the deterministic, like just appear here ones or zeros in the probability. And you ask which ones is convex of this. Okay. Yeah. So that's why it's the same. But actually here we show that it's the same in general semi-ring. Maybe the theorem will be trivial if you do this for positive, non-negative reals. It's okay. Like, yeah. In general. Yeah. Yes. Another semi-ring. Yeah, the Boolean. Yeah, what? The convexity or? Yeah. But actually, it's good this because in the Boolean we have also the. Actually, maybe I didn't mention here. You are from strongly contextuality also. Strongly contextuality. Yeah, this will be good in this because actually there is a strongly non-invertibility, strongly, and this match together. And in the Boolean, it's important to know, like, because if you have like the reals, the positive real, non-negative real, you down to the Boolean, there it's just this important to know the strongly contextuality and things match together. Strongly contextuality and strongly non-invertibility. So that's why important in the Boolean. Yeah. But no, for me, I did it abstractly. Like I don't have I come from abstract mathematics, so that's me. I don't know many semi-rings. Yeah.
I'll have one more, but maybe it's too applied then. So in the foundations community, there's a nice work about the contextual fraction. I don't know if you see
yeah, of course. Yeah.
So
this is what I'm talking about. Yeah. It's talking about like strongly contextuality when the contextual fraction is 0 or 1. How SU defines this? Yeah.
Can you generalize that quantitative notion to something more?
Yeah. In the you will find the invertibility fraction. The invertibility fraction, it's in some sense, is generalization of the contextuality fraction. Of course, when your outcome have group, actually, like, because we take, here is the difference, like in the before we talk when we talk about convex category, we talk from the convolution, from the Kleisli, sorry. Here when we talk this proposition, sorry, yeah, in this proposition, it's come from the Kleisli composition. The composition, but here we need the outcome to be a simplicial group. But always you can do this. Like if the outcome is finite, you can say it's the nerve of Zn. Okay, then you have this. Yeah, you can see it's in the paper. There is the notation of fraction invertibility. This is actually generalize the fraction contextuality. Some sense. Yeah.
Okay, well, thank you very much.
Thank you.